This question, we have a girl at the edge of a cliff, familiar situation, throwing a stone vertically upwards. So that means it's a one-dimensional projectile situation. It lands in the sea below. It leaves her hand with a speed of 12 meters per second and a height 30 meters above the sea. So depending on how we want to set this up, we could set this up as this is the 0 and this is minus 30, or we could set this as 0 and this is 30 as our initial positions. So we have our acceleration of 10, ignore air resistance, what we'd expect. The maximum height from sea level. So that means 0 is down here, reached by the stone. Well, the maximum height we know is going to occur. The projectile is going to take off and it's going to slow down, and its maximum height will be when the velocity equals 0. So we could take note of that here. Max height, v equals 0. So v equals at plus v0 minus 10t plus 12. That is v, and we want it to be 0. So 10t equals 12. T equals 1.2 seconds. That's how long it will take. But we want to know how high it will go. Now, there's a couple ways we could do this. We could jump right to our z formula. Z equals 1/2 at squared plus v0t plus z0. But oftentimes it's easier to start with the average velocity. By definition, the average velocity is delta x over delta t. In this case, delta z over delta t. We're looking for delta z, so delta z is v bar delta t. Well, we know delta t is 1.2. Oh, what's the average velocity? Well, the average velocity is delta x over delta t. It is also v plus v0 over 2 when a is constant. Well, we know that v bar is equal to the final velocity, which is 0, plus the initial velocity, which is 12 over 2. So the average velocity is 6. So we have 6 times 1.2, which is 7.2 meters, is our delta z. And so that's from here, it's going to go 7.2 meters. From sea level, it is 37.2. So we're looking at 37.2 meters equals max height. And to go further with that, we remember that the delta z is z minus z naught. And if we want to know the instantaneous height when it's at a maximum, well then z would be equal to delta z plus z naught. And delta z we figured out was 7.2, and z0 was actually at a position of 30. So the instantaneous z is 37.2, even if we carried it through with the, if we wanted to show it algebraically. The second question is we want the time it takes for it to hit the sea after leaving the girl's hand. We could go right to this and write out our equation. Z equals 1/2 at squared plus v0t plus z naught. We want to know how long it takes for the ball to get to the sea. Well, we know how long it takes to go up is 1.2 seconds. And through symmetry, we know it takes 1.2 seconds to get back to that original height. So really, we're in a situation where this could be just the ball being thrown downward with an initial velocity of minus 12 meters per second. We could set it up either way to see, which would be the easier way to do it. So if we set time equal to 0, then we have 1/2 minus 10 t squared plus 12t, and our z0 is 30. And we want to know when that is equal to 0. So 0 then is minus 5t squared plus 12t plus 30. And now we have to solve this quadratic for t. If we had set it up the other way, we may find it'll be a little easier to solve, or maybe not. So in the second situation, we would start it from here. So we have minus 1/2 10t squared, where v0 in this case now is minus 12t plus 30 is z. We want to know when that equals 0. So 0 is minus 5t squared minus 12t plus 30. So it's not any easier. Well, what if we set this equal to 0 and minus 30? Well, we would have then minus 30 equals minus 5t squared minus 12t. So in all of these situations, we're ending up with different equations, but they're all equally difficult to solve. T, when we solve it as y equals any one of these equations, we end up getting, in this case, where we started with a position of 30, we get 3.9 seconds. And in this case, we get t equals 1.5 seconds, excuse me. Now, in this case, we have to add 2.4 seconds for the time up, 1.2, and another 1.2 down, to give us the total 3.9 seconds. The graph, we want to know how the speed varies. And as I said in the instructions, we want to include the critical values. So we're looking for the speed, how the speed varies. And that's key because that means not velocity. From it leaves your handle just before it hits the sea. Well, it starts at a speed of 12. The accelerate, so we can read velocity time. The slope is delta v over delta t, which is acceleration. And so that's a constant minus 10. It goes to 0. And then it increases again because speed is always positive. And then it continues to increase until it hits the water. So this happens at 1.2 seconds. At this point is 2.4 seconds. And this point is a cumulative 3.9 seconds. This representing the 1.2 up. This the 1.2 down to the same height. And this the 1.5 to cover the rest of the distance for a total of 3.9.